All right, welcome to the lunch video. I work with people across time zones, so we figured out that that 12 o'clock noon my time central was the best time for a meeting I've got. So I'm going to take an early lunch and be flexible so I'm going to do my video now. All right, and where we left off, we were learning more about communities. We finished an exercise where we straight up removed the communities from the routes because communities are optional transitive issues, transitive BGP path attributes. And one thing to remember too is they're not necessarily BGP path attributes. In this case, yes, because we applied to the PGP they are, but communities can be applied to any protocol. So they could also be a OSPF attribute, a ISIS attribute. It's just a marker, an identifier you can add to any kind of route. You can even add them to static routes. All right, so in this example here that we finished, we simply removed the policies because they're the tagging, the BGP community, we just removed that from the routes because they're optional transitive routes, so they get passed on unless you remove them manually through a routing policy, and it would be a, yeah. In the next example, we learned about extended communities, which uses a extra byte, normally BGP, or which uses an extra 4 bytes. Normally BGP communities strings are 4 bytes, the same length of an IP address, 32 bits. But if you want to use them for VPNs, that's not enough bits to have them be useful in that case. So you can use extended communities, which give you double the space. You get 64 bits to work with. Finally, we did another policy where we took an action based on the community tag. They were tagged as routes that a routing table would, so they were advertised through through a topology with a redundant connection, so that a router would be receiving the same route from 2 different routers. So we configured a well-known discretionary attribute called local preference to have that router receiving those duplicate routes decide which route to use based on configuration we added upstream and not on that route. So to do that, we assigned a community attribute to all those routes. And then before they were advertised over to that final router, we did an import policy to modify the local preference as they're being added to the routing table here. And the local preference is a well-known discretionary attribute, so it's included in every update message. So that was sent out to router, the router that we wanted to prefer a particular path over, and we saw that it did that. So that's kind of a neat thing you can do with BGP communities that's kind of unique. Like you don't have to log into a particular router. You don't have to say, I've got to log in and manage this router if I want it to prefer this path over this. You can do that only by managing other routers, by adding a community tag, and then by manipulating BGP path attributes to have this make decisions based on the information it receives and not based on any information configured on it originally. It's kind of a nifty thing you can do. All right, so the final one is we're gonna learn about configuring BGP large communities. This example shows you to configure optional transitive path attribute, a 12-byte BGP large community that provides the most significant 4-byte value to encode autonomous system number as the global administrator, and the remaining 2 4-byte assigned numbers to encode the local values as defined in RFC 8092. You can configure BGP large community at the edit policy options, community name members, and edit routing options, static route, IP address, community hierarchy levels. The large community attributes has 4 fields: large, global administrator, assigned number. So I'll just open this up, maybe skim it through, not necessarily read all of it. Looks like I had this open before. In this example, device R1 and device R2 are OSPF neighbors in autonomous system AS64510. Device R3 has an external BGP, eBGP connection to device R1. Device R2 has customer networks in the 172.16/16 address space, simulated with addresses on its loopback address, LO0. Device R1 has static routes to several 172.16.x/24 networks and attaches regular community values to these routes. Device R1 then uses an export policy to advertise the routes to device R3. Device R3 receives these routes and uses an import policy to add large community values to the routes. All right. So let's get on with configuring. Maybe, oops, go back to where I was. There we go. And then maybe take a brief look at this. Looks like it's a pretty small one. But yeah, I guess it's probably not going to be anything new in there. So let's get to configuring this. And I think I actually do want to use a management server for this. We're going to need to set up a management network first, of course, but we can do that using the configuration in the example. We'll just need to have a better sense of what configuration does that and what does not. So let's start, instead of just configuring everything in here line by line as it's given, let's break it apart and configure only what we need to have a management network set up in this autonomous system. So run show int terse pipe match g dash. So we've got 0 and okay, so it looks like it's aligning exactly perfect. It doesn't match the topology. That's definitely not worth a downvote. It might make things harder though if, no, it looks like it does align though IP addresses. So that's actually my preferred thing. Yeah, if they're using the IP addressing I'm using, that makes things really, really easy. Perfect. So now let's do edits interfaces 001, unit 0. All right, perfect. So we're definitely going to need those two to have a management network, of course. The other thing we're going to need is a dynamic routing protocol. So it looks like they've only got it set up. Aha, yeah. Because of course, these are 2 autonomous systems. So you're not going to be able to manage. If I work for AT&T, I'm not going to have management access to Comcast because they're in 2 autonomous systems. And we can even just do a quick Google for largest BGP AS. So a ranking of the largest autonomous systems. And we can see what kinds of companies are going to fall under. So level 3, Telecompany, Cogent, GTT, NTT America, Telecom, Hurricane Electric. So never heard of, I think the average person will have never heard of any of these companies. Well, here's Comcast, we'll have heard of that. But they're all different companies. You can see a lot of them are international companies. So it's, if you're in autonomous system 3356, you're definitely not going to be able to access autonomous system 1299 because they're owned by completely different organizations. So likewise, in our example, if we're in autonomous system 64510, it's really kind of unreasonable to expect to be able to manage any device in 64511. So I'm going to be using 2 different management servers in this one just to keep that as realistic as possible. I, of course, could set up management across the ASs, but I'd have to stray pretty far from the spirit of this original documentation. I would have to add GE001 to this. Okay, so let's see here. Yep, so this is going to be required. You'll see, hopefully, that the configuration required for management is quite tiny. And hopefully this will kind of, yeah, and hopefully this will kind of drive home the idea that there are different kinds of configuration and they're all built on top of each other. So, and kind of, you know, how things, it's like when you're building a house, you have the concrete foundation, you have the walls, you have the roof. So the concrete foundation for anything you do in networking is, of course, the IP addresses here, and then you build on top of that with your routing protocols. And then even then, this is all you need for a management network. But if you want to send routes across autonomous systems, then you're going to need BGP. And if you want to, so it's kind of, I think, a good example of how concepts in network engineering build on top of one another, just like they do in just regular route math. And how simplistic concepts can be when they're separated from another. That's another thing that's always good to see, because if you only see this whole thing, it's like, oh, this is such a nightmare, it's so complex and stuff. Well, it's really not that complex. It's just a bunch of things that aren't so complex all piled together. So yeah, it can get complex in that case. So I definitely want to kind of slow it down and only show the parts that have to be shown. So if my intent were to set up a management network as it is right now, I would not want to configure BGP. And in fact, I did kind of get ahead of myself a little bit and configured this port here, GE001, facing the eBGP. That's actually not going to be a necessary port to configure, so apologize for that. I will go and delete that because that is a little bit of extra complexity that's really not going to give the right result that I want in showing that it is not a huge challenge to configure just simple local management to your network. Okay, so here we go, as stripped down as possible. All we've got is the description, make it easy for us, the IP address, and then we've got that into OSPF. So on router 2, we're going to need a similarly easy configuration. All right, so hopefully we'll be learning some routes through OSPF soon. So show route protocol OSPF. It looks like so far we don't have any. Let's see if we've got the neighborship up. Okay, so we do have the neighbor in full state. Let's think more about our topology and what routes we might be missing. So it looks like our topology is just a point-to-point topology. So at this point, there actually is no need for a routing protocol. So we're really not missing any routes because we don't have any routes that would require a routing protocol to be discovered. But of course, that's all going to change once I add the management server, because then that network that the management server is connecting to the autonomous system with is going to need to be known by all the other devices. So let's add that management server in. Hopefully it takes a while. I might need to get a new image. This is kind of, I'm not even sure where this really came from, and it's not the greatest. So let's go with the recommended solution. So I'm going to be installing it from the server. Let's see here. So hit next. Then we want a guest. And yeah, maybe one of these would be, aha. So here we can get, so this I think is what we've already got here. So it's not like this just came from nowhere. It was the one that was included here. Ooh, it's kind of fun. We get AttackX GUI. We get Docker best. Or what else do we get? So we get a WordPress. We get a Windows server. We get all sorts of fun stuff. Aha! Here we go. We get Python. So scripting hosts. Lots of looks like we got a monitoring tool too. So a lot of really interesting things to play with as well. So I wonder if there's a way, I might need to take a break. So I wonder if there's a way I can just pause. I can pause the share, but I don't know if I can pause recording. Oh, I can pause recording. Okay, so I might need to take advantage of that and just pause recording for a bit and come back. So you just see like a jump cut. Yeah, you know what? I'm going to do that. So I'll be back in a bit, but you'll just see a jump cut because I will pause the recording. All right, so hopefully that was a pretty seamless jump cut there. Just needed a break. So last time, before I hit that pause button, we were looking at all the pretty cool extra services we've got to play around with. We've got a DNS server here, AAA server. We've got a, looks like even like a F5 load balancer we could even play with. It's definitely very interesting. A full Kali Linux machine with the GUI and everything, or we can just have the CLI only. So we can do network attacks, DHCP spoofing, our poisoning, that sort of thing we can emulate. We got a network automation server that's already there. So lots of really cool stuff to play around with. TACX server, example website. Yeah, really cool stuff. Okay, but so it looks like the network automation server did show up. And it takes a while, but let's cable it up. Okay, and I'm going to put it on GE009. So I've got to set that port up. Let's go with 172.19.0.1. We'll choose kind of a unused space. I don't expect this to be used. So now we're going to need to, of course, configure the server as well. Hopefully there aren't any issues with that. So while that's coming up, I want to take a closer look. Oh, it looks like it came up instantly. Okay, well, yeah, I'll configure it. So ifconfig help. So ifconfig interface AF, and then we can add address and prefix length. So let's go interface, and let's just do an ifconfig. Okay, so ifconfig eth0, and then inet. And now we're going to be adding the address. (172.19.0.2/30). Oops. Oops. Is it -- net? See, the thing is, the last time here we go, address family default. So ifconfig inet0 add didn't work. So it gives the usage. So it looks like isconfig, and then we've got -a, we've got -v and -s. So I don't know what -a does. It doesn't tell you anywhere. Maybe that's address family, but it says interface address. So the interface is definitely going to be eth0. And then this is the address. Aha, so we did set an address. So let's do ifconfig. Perfect, so we've got our address on there now. We need to set up a default gateway, however. So let's do a route. So yeah, see how it's missing the gateway there? We need to add that in there. So ifconfig help. Is there any option to set up a default gateway at all? Netmask. destination address, HW, looking for something like GW, gateway, something like that. Maybe the netmask command. So netmask 255. And now maybe I can put it because of this destination address. Oh, yeah, we still don't have the gateway here, so we've got to figure out a way to add the gateway there. We can see that the help menu leaves a lot to be desired. And it's not even usable at this point. Okay, so we can ping there, but we can see the routing table really leaves a lot to be desired because this gateway is not filled in. So if there's going to be any traffic, if I were to ping 8.8.8.8 right now, which is the Google DNS, we can see network is unreachable because there's no route for it and there's no gateway of last resort. So let's see if we can use the syntax in this route command and set up a gateway of last resort. So we definitely want to add a route to this. So here we go, add. So route, add, and it's going to be, can we have any help here? No help. Yeah, so can only get help. Oops, I did router instead of route. Okay, so now I can get some more help, but unfortunately it is not specific to the add command. So yeah, the syntax of this is just represented by ... So it kind of assumes you know what the syntax is. But as we know, if we're really familiar with networking, there are multiple syntaxes you can use when defining a route. You can use the CIDR, you can use a keyword like netmask and type out the whole subnet mask. And then for the default gateway, is it going to be gateway? Is it going to be GW? We really can't, a help menu that just gives you 3 dots for the required syntax of a command that can take multiple versions of syntax is really not useful at all. But you can't downvote a Linux image. So let's see here, git add, and then we need to, we're gonna add, so the gateway of last resort, so 0000 slash, and then the network address is going to be 0 because this is going to be, we want any network at all. So and then oops, no such device. I think I remember before you have to do this -net. No such device. So yeah, I don't remember, unfortunately, how to use this. I kind of wish I had a different server, because this one is needlessly difficult to use, because you can see the help menu is so unhelpful. But okay, so now we're getting, aha, so here we go. Now we've got some help that is actually more useful here. Thank goodness. I don't know where this came from, but I am glad to have it. So now we can even see this .-net is going to be really useful. Now we get the next parameter is going to be the target -prefix, and now we can see this gateway command. So boom, oh, invalid option. Oh, I did new instead of net. Boom. So now if I do the show route, oops, or if I do the route as it is on Linux, I can see I've got a default route. So if it doesn't have a route for it, 8.8.8.8, it will send it out through to that gateway at 172.19.0.1. So I'll no longer get a destination host unreachable message, or it looks like I will get a destination net unreachable. You can see that it's quite a bit. Oh yeah, exactly. So I no longer get a no route to host message. You see, I got that up here. Where was it? I think it's, I wish I could find it. If I had secure CRT, I could search, but I can't do that here. Why don't I remove that and just, because this is going to be something important to know about. There we go. So now if I ping 8.8.8.8, network is unreachable. But if I add that back in, destination net unreachable. So it actually did. And if you see where this comes from, so we made it to the gateway. So without this route in here, we're going to get this network is unreachable message from ourselves, because we don't even know what to do with it. Where are we going to send it? But now that we have a gateway of last resort, even though this 8.8.8.8 is not in the routing table, we know that we can send it to this gateway here. But that gateway replies back with the same message we got on ourselves when we didn't have a route in our table and had no place to send the route. Because if we go over to that gateway, which is going to be router 2, and do a show route, you can see 8.8.8.8 is not in the routing table. And not only that, there's no default route there as there is here, where if it's not in the routing table, go and do something like that. So that's why we get that message back. And that's the difference between having this route and not having this route. If you don't have a gateway of last resort and you don't have the routing table does not know where you're trying to ping, you're completely out of luck. But if you do have one, you can ask that gateway of last resort. If they don't have one, you're out of luck too, but they will tell you. And then if they do have one, then you're all set. So gateway last resort, that sort of thing is really a fundamental concept of network engineering. So if anyone is watching this and doesn't have that mastered, I hope this has helped. But for now, we are going to be able to have management to these devices. We're going to be able to connect via those interconnect links. So I should be able to ping right now 10.0.0.2, perfect, and .1. That's interesting that I could ping .2 but not .1. And I should get the Oh, you know why? So, okay, so let's do a 3, 2, 1. All right, so hopefully you took a moment and you thought about why I cannot ping this router here. So let's trace the path that it would have taken. So it started at the server here, this 172.19.0.0/30 route. Then it travels over to R2, and now it travels over to R1. So let's take a look at R1, the routing table. So there it is, 10.0.0.1. It's a directly connected route. It's in fact configured on an interface. So why can't I reply back to the management server at 17.19.0.0/30? Well, do you see a route for that? There's nothing in the table. It can't do it. So we get back just a timeout. Like, it knows what to do when it gets here, but this is the, now here's another question. Would we get a timeout from router 2 right now if we tried to ping the management server? Yes or no? 3, 2, 1. No, we would get the destination host unreachable message because it does not have this in the, and this is router 1, not router 2. So let's try that. .2 is the one on the Linux server. Aha, no route to host. So hopefully that looks really familiar. It's just like this one right here. We don't have any route to that. We have no gateway of last resort. So it's just going to be no route to host, and it's going to come from this device itself. Whereas if it would have a route, but that route then led to nowhere, it would come from wherever it made it eventually. But you can see that a good question to ask might be, oh, well, why am I not getting the no route to host message then, like I did up here when I added the route, pinged it, and then from my server here, I got the destination net unreachable. Well, if we go to that server and we look at the routing table, which I already had up here, we can see we have a route there. So we do have the means to send this destination route is unreachable message back to the management server. So that's what the route's going to try to do. But when we ping that .1, it'll make it all the way across to this router. But when it tries to respond back, it's got no route to host. So our ping just sits and waits for a response, but it's impossible for it to get a response back because the routing table in R1 doesn't have the means to do so. So as kind of a final point, I will sniff the link here, and we will see that those ICMPs are making it to router 1, but they're unidirectional. They're only going to source from router 2. Well, they're only going to source from the management server IP, which will be the MAC address of router 2. But so that's what we'll see. Yep, and we can see 10.17.0.2 over to .1. No problem. All day it's going to make it there. It's just not going to make it back. If we look deeper into this, we notice that the MAC address, let's look at the MAC address of the ETH0 on the management server. So IF config. So MAC address is going to be CE97BB 0C A635. So it doesn't match. Well, that's because as a packet moves through a network, it uses its layer 2 addressing to move across the link or to move across layer 2. But after it gets routed, that's when it uses its layer 3 information, and it actually strips off the layer 2 information. So we can go here and we can have two captures open and we can see those same ICMP messages. But in this capture, we will see that even though the source and the destination IP addresses are still the same, the MAC address information will be completely different. So, yep, and here's the MAC address. So it makes it to there. And the other thing we notice that is going to be kind of unusual. So here's the destination MAC address, but our destination IP is the port on router 1 where that IP address is configured. So show in terse pipe match GE dash. So here it is. So 3, 2, 1. Okay, hopefully you've taken a moment and you can answer me the question, is this MAC address on this port here, if I do a show int G000, is it going to match the destination MAC here? I'll give you another chance. 3, 2, 1. So no, it's not. We've got the MAC address it's the same vendor as Juniper, but it's going to be F302 instead of 480B. So I'll give you another chance. Where is this MAC address going to be? So we know the destination IP is going to be this R1 interface 000. But where's the destination MAC? 3, 2, 1. Okay, so the destination MAC is going to be that gateway of last resort. So the route, this gateway here, that IP here, port GE009. If we do a show int GE009, we can see the MAC address is 480B. So EB480B, that's the MAC address. And that's because whenever you're sending a packet to a destination that is at on a different subnet than the source, it sends it either to whatever specific longest match route it has in its routing table, or if it doesn't have a route at all, or the gateway of last resort route is a longer match, it will send it to the default gateway or the gateway of last resort. And a little bit about those terms. Default gateway, we were talking about like a layer 2 gateway. It's a address. It's a command that is used a lot on layer 2 devices. You'll set the default gateway, but a gateway of last resort, those are set on layer 3 devices, and those are going to show up in the routing table. Default gateways aren't really going to show up in the routing table because layer 2 devices don't even have routing tables. They have MAC address tables. But you can see that, sure enough, it is the default gateway MAC address, even though it's the GE000 on R1 destination IP address. So hopefully, if somebody is watching this, they are not super confused. I have another question that might help make things less confusing. So the question is, here's a packet with the same destination source address and the same destination and source address. So the MAC address is going to be the same. You might have looked at it already, but I'll give you a chance to answer yes or no right now. 3, 2, 1. So of course not. They're going to be completely different. And you can see both the source and the MAC address and the destination MAC address are completely different. And that's because as a packet travels through a topology, once it reaches a router and it is routed based on its layer 3 information, its IP addressing here, this layer 2 information that got it across the wire or across the layer 2 switch in the broadcast domain or the VLAN that moved it from host IP to host IP within the same network. This information is used to do that. That information is no longer necessary because we're going to have a new network. So that information gets thrown away and replaced with new information that is now relevant to move it from host IP to host IP within the new network it was routed to. So hopefully that is really clear. I think this was a good lesson refresher to that. This is a concept that I have, I really think I've like mastered really, really well. So I'm glad to teach it. Hopefully someone, if they see this video, will get a lot of value out of it. And let me know in the comments if you want me to elaborate on it, because I think it's one of the concepts I definitely understand the most. Just kind of basic routing and switching. I mean, I have the CCNP in routing and switching, and I graduated from a networking academy, so I definitely understand those concepts very well. So just let me know in the comments if you want me to elaborate some more. Unfortunately, when it comes to passing this test, it's not going to be something that I think I will require a lot of practice on. So I think that's going to be it as far as that is concerned. Talking about that in further detail, that's going to have to do. All right, so moving on, we've got, I think, a good understanding of that. So one thing I think I will do, though, is instead of managing the device through its interconnect address, so we can definitely ping the devices through their physical ports, but I think I would prefer, and oops, wait a second. Let me go on router 1 and look at something. Oh, and actually I'm out of time. I didn't even realize that so much time had passed. Oh, right, I didn't. Okay, so kind of the whole point capstone of what I was talking about, I didn't actually go and do. So you can see show configuration pipe display set pipe no more. So yeah, I forgot to add the that interface to OSPF, which is kind of where I was going with that whole rant. I guess I never kind of completed the thought, unfortunately, but hopefully I'm doing that now. And we'll see that pop up in the OSPF table. There it is. And now if I ping that, we'll get a successful ping. So I've got to cut the video short there. Hopefully this was really helpful. We learned about just basic routing and switching and how the MAC address information is specific to the subnet it's on, and it is stripped off and re-added when it's routed between subnets by a router. We learned about kind of the basic stripped down config that is required for management to a network. We learned more about Linux and configuring IPs, gateway of last resorts, that sort of thing. And then we started the video by continuing on with this BGP large communities session. So hopefully you got something out of it. Stay tuned for the next video.